Hello, folks. New chapter, new topic, a refreshing start for some of you. This chapter 8 talks about vectors. Now, we're going to take a small break from the trigonometry that we've been dealing with, talk about vectors, something called parametric equations, and what that looks like. And then next chapter, chapter 9, we're going to kind of put things back together again and incorporate a little bit more trig and the unit circle again. But for now, I hope you'll find this kind of as a refreshingly different topic than what we've been dealing with lately. Kind of physics-esque in nature. You've dealt with vectors in physics, or if you haven't, you will soon. Hopefully you might remember this about vectors. They are different than like a typical line segment or ray in geometry. Vectors have magnitude and direction. So vectors have magnitude and direction. Magnitude is just a fancy word for length. Length is always positive. Length always positive. And it can be found by, found by doing a few different things. But the other main thing is absolute value. Right, if you have a segment along the negative x-axis at -7, it doesn't have a length of -7. We take the absolute value of that, it would have a +7. Direction, we're not specifically talking about like up, down, left, right, or north, south, east, and west. But in this case, direction actually is going to mean the angle between the vector and the positive x-axis. The angle between the vector and the positive x-axis. Okay, so let's draw a couple of examples of what we're talking about here. So if I have the vector from point P to point Q, as it's drawn right now, this is a geometric figure called a line segment, okay? What's going to make it a vector is if I put direction to it, so I put an arrow. Now, again, I'm not talking about a ray, right? In geometry, a ray starts at one point and then extends forever in the other direction. This vector starts at P, and then its end is the tip of that arrow. So this does not denote that it goes to infinity. You could also call it, so sometimes you could call it by those 2 points. We can call this vector PQ, which would look like this, PQ. And then the vector symbol is kind of like a line symbol like this, except we're only going to do the top part of the line, of the arrow rather. So instead of being a full line symbol, the vector symbol will just be a top part of the arrow. Okay, so that's a vector. You can call it vector PQ. Sometimes you'll see a small lowercase letter to the outside of a vector. So you could also call it vector A, denoted by a lowercase a with the vector symbol on top. So either one of these would do. Now, the idea with direction also has an impact on the name. You can't just name it vector QP, okay, because that would imply that the arrow were in the other direction. So in this case, we call P the initial point, and we call Q the terminal point. So that's where your vector stops. So when you name vectors, the first letter always has to be the initial point, P to Q. Okay, now let's talk about that idea of direction for a second. Direction, so if I actually put a vector on a coordinate plane, and let's call this vector vector B, like this. So vector B, even though it's like pointing what we would consider as northeast if this were a typical compass, its direction, by definition, is the angle between the vector and the positive x-axis. So I drew this to where it's about a 45-degree angle. So then we would say that the direction of vector B, I think I said angle B, I'm sorry, I meant vector B. The direction of vector B is 45 degrees. Okay, so that's just a little bit of basics about vectors and their positions and things like that. Now, this may seem a little bit obvious, but we need to discuss it anyway. In order for vectors to be equal, they must have the same magnitude and direction. Okay, they have to have the same magnitude and direction, so not just one or the other. Okay, so maybe I can draw, I'm not going to be perfect in drawing this, but hopefully enough so that you get the idea. If I call this vector x and this vector y, these would be considered equal vectors. Notice they're also parallel to each other, right? Because if they have the same direction, that means that they're going to have that same angle to the x-axis. So they'd be parallel to each other. And again, the same length as well. So they have to have the same magnitude, same direction. Sometimes that's confusing, so you have to pay very close attention to the arrows, because an example of vectors that are not equal could be something as simple as this vector A and this vector B, which appear to have the same magnitude, but have obviously completely opposite directions. Okay, so there's an example of vectors that are equal versus vectors that are not. All right. Now, geometrically, we can add vectors. Now, notice I said geometrically, so I'm not really talking about numbers quite yet. But when we add vectors, then we say the sum of two or more vectors, not sum, the sum of two or more vectors is called a resultant. Okay, so again, I'm going to be adding these geometrically. In doing so, there are two scenarios. Okay, I have what's called a parallelogram method. I say I as if I came up with this. I did not. There is something called a parallelogram method, and there's another thing called the triangle method. So basically, if I ask you to add two vectors, so let's draw the vectors first before we talk about the methods. Perhaps I want you to add vector Q like this, and vector P like this. So if I want you to add those vectors, they have to maintain the same direction and they have to maintain the same magnitude. Okay, now adding them, if they had length, is not as simple as just taking their lengths and adding them together. It's also not as simple as taking the average of their lengths. Okay, adding vectors is a little bit complicated because you take into account its magnitude and its direction. Okay, so in doing so, geometrically, we have two methods. First is called the parallelogram method. So let's copy down our vectors again, but in a position that's going to allow us to draw a parallelogram. So again, try to do your best to make them the same lengths as what we drew up there. So if that's vector P, and then if this is vector Q, the parallelogram method says if we add these vectors and we draw a parallelogram, so then if I create, draw some dotted lines here to where it would make it a parallelogram, then this method says that the resultant would be from the same vertex that Q and P have, that same initial point, to that opposite corner. So this blue vector would be the example of vector P plus vector Q. So again, not double P and Q, or not the, at P and Q added up together, not the average of them. It kind of takes into account their distance, their length, and their direction. There's also a triangle method, which this method is also sometimes called tip to tail. So tip meaning the where the arrow is, right? The terminal point, and then the tail being that initial point. The triangle method, again, is going to maintain the magnitude and direction of the original vectors. So again, let's draw vector P first. But instead of putting its initial points along with the initial point of Q, the tip to tail method says, let's put vector Q on the other side. Again, maintaining its magnitude and direction. So again, this is the tip, that's where the tip to tail comes into play. So if that's vector Q, the resultant would be, again, triangle method, the resultant would be this blue vector here, which is vector P plus vector Q. Again, I'm not a perfect artist, and neither are you, but as you look at that, those blue vectors on each of the methods are pretty doggone close to each other. Okay, so that's a little just dabbling in 8.1, which is geometric vectors. Okay, we're now going to move to algebraic vectors. Okay, so you can call this now 8.2, algebraic vectors. And this is where we're going to actually assign numbers to the coordinate plane and put vectors on a coordinate plane. Now, before we do so, we need to define some things. Similar to the unit circle, like when we say that an angle is in standard position on the unit circle, we know that it's in like that 3 o'clock position, right, out to the right at 0 degrees. Algebraically, for a vector, we say that a vector in standard position has its initial point at the origin. So as far as direction goes, we don't really care where the direction is, but all that it requires is that the initial point needs to be at the origin. Okay, another word to define is a unit vector. Okay, the unit vector might be exactly what it sounds like. How the unit circle has a radius of 1, a unit vector has a magnitude of 1. And we have 2 unit vectors. Okay, well, actually, technically, there's an infinite amount of unit vectors because you can have any vector with a magnitude of 1. But there are going to be 2 specific kind that we talk about. Particularly, if there's a unit vector along the x-axis that's in standard position, then it has a specific name in the algebraic vector world. It's called vector I, which we're going to talk about this part in a second too. We say it is represented by the ordered pair 1, 0. Now, notice this is not typical ordered pair notation. You don't use parentheses. You use, it's what looks like a greater than and less than symbol, but that's not exactly what it is. I don't know if it has specific names or not. Okay, so there's a unit vector along the x-axis. We also can have a unit vector. Oh, where did my font go? There it is. Unit vector along the y-axis. In true mathematical alphabetical form, the unit vector that's along the y-axis is called vector j. Oops, I didn't dot the j. And its coordinates would be 0, 1. That would be its ordered pair. Okay, and these look, I mean, exactly what we say they should look like. If this is your coordinate plane, you know, counting by 1, 2, and I'm zoomed in a little bit here, but the unit vector along the x-axis in standard position would be like this. So we'd call that vector I. And then along the y-axis here, we'd call that vector j. So now let's talk about that notation that I was just writing. Basically, even though they're not coordinates, we can use an ordered pair to represent vectors that are in standard position. And that's important, so let's write that. Can use an ordered pair to represent vectors in standard. Why did the font get small? To represent vectors that are in standard position. Okay, so if a vector is just floating out in the middle of your coordinate plane, we can't use this notation. So the key is they have to be in standard position, meaning that its initial points must be at the origin. So I want to talk about what a vector is and what that ordered pair notation is and what it is not. So I want to talk about the difference between the ordered pair that we know and incorporating vectors. Okay, so let's just sketch out a very small coordinate plane like this. My dogs are very whiny at the moment, and they don't realize that I'm not going to help them. Okay, so if I ask you to graph the ordered pair 4, 1. So this is just back to what you know about math, period. If I ask you to graph an ordered pair, you start at the origin. The first number tells you that we're going to the right 4. The second number tells you that we're going up 1. And voila, bada bing, that is the number 4, 1, or the coordinates 4, 1. If you're going to graph a vector that has this notation, 4, 1, that means starting in standard position, it starts at the origin. We still go to the right 4 and then up 1, but the vector is the actual magnitude between those 2 points, so the initial point and final point. Okay, so a minor detail in notation changes the picture drastically. Are we talking about just the point, or are we talking about the vector that starts at the origin and goes to that point? Okay, next thing we want to talk about is magnitude. Now, I said that magnitude is found by absolute value, and that point was just to bring that if you have a vector in the negative quadrant plane, we have to take the absolute value of it because length is always positive. But if I'm looking, so you can even look at this example over here that I drew, or actually let me draw a new one. So if I just have a vector floating in my coordinate plane somewhere, and let's call it the vector, let's say that it starts at P1, and it goes, its terminal point is P2. And again, it's just on my coordinate point somewhere, on the coordinate plane somewhere. I don't know exactly where that might be. So let me just give that arbitrary coordinates. Let's say P1 is at the point x1, y1, and let's say P2 has the coordinates x2, y2. If I ask you for the magnitude, in other words, length, of P1, P2, there are a couple of different things that you could do. So I hope your wheels are turning. Maybe you're thinking about some options. There are 2 options, but they're actually kind of one and the same. Option 1 is that we can use the Pythagorean theorem, right? If I knew, basically we can take any kind of segment like this, not a segment, any kind of vector like this, and sketch out the horizontal and vertical distances, create a right triangle, voila, use the Pythagorean theorem to find the length. Now, how can I represent that horizontal and vertical change? Well, this vertical distance is along the y-axis. So I can find that vertical distance by calculating y2, right, whatever the y value is of P2, minus the y value of P1. So it's going to be y2 minus y1. And then I can find the horizontal distance by doing the same thing. I can calculate it by doing x2 minus x1. And then if you kind of do some work with the Pythagorean theorem, it's how we arrived at the distance formula. Okay, so now we know distance is equal to the square root of all that kind of good stuff. So if I want to say distance particularly of this vector, then I would say the absolute value of P1, P2, so the distance from P1 to P2, is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. And again, x2 minus x1, if I'm looking at this triangle as the Pythagorean theorem, That would be like a, b, and c. So this would basically be the square root of a squared plus b squared equals c squared. But again, I solved for c, I took the square root. So it depends on how, I don't really care how you think about it. It is the Pythagorean theorem / distance formula. So let's do some examples. It's important that you write these examples. You can shorthand words if you want to, but the assignment that goes along with this is going to have the same vocabulary. It's going to ask the questions in the same manner. So I want to make sure that you write the questions the way that I do. So it's going to say, write the ordered pair that represents the vector from the point, let's do D, point D at 2, -3, to point E at -4, 2. Then find the magnitude of vector DE. Then find the magnitude of vector DE. So again, make sure you're using vector symbols where I am anytime we're denoting a vector. So it says, write the ordered pair that represents the vector from these 2 points. Visually speaking, what we have going on here, as if we sketch out a coordinate plane very quickly, and I graph those 2 points. So D is at about 2, -3. So there's point D. E is at -4, 2. And it doesn't have to be perfect. I'm just trying to sketch what we're looking at here. Again, we have direction, right? They're telling us the vector is DE, so the initial point is at D, and then it's going over to E. So it says, write the ordered pair that represents the vector. So I want one ordered pair. So I know where the point D is located. I know where the point E is located. But how can I represent this one vector using one ordered pair? Well, essentially, we're going to do just like we talked about with that Pythagorean theorem up there, is we want to find the change in x and the change in y. Okay, so then we can say that vector DE, its ordered pair can be written as x2 minus x1, right, which this is delta x if you want to call it that. And then delta y will be y2 minus y1. Again, vector notation uses these arrow kind of things, I guess, instead of typical parentheses. So then when we plug in our values, x2 minus x1, typically it doesn't matter, like back in geometry when you did distance formula, it doesn't matter which coordinate you call the first one and which one you call the second one, but because vectors have direction, it is important that we call D, since D we know is the original or the initial point, that we call this coordinate x1, y1, and that E is called x2, y2. So then when we plug in those numbers, x2 minus x1 will be -4 minus 2, and then y2 minus y1 will be 2 minus -3. And then we just got to simplify these. So -4 minus 2 will be -6. 2 minus -3 changes to plus a +5. So then we can say the vector DE can be written as the ordered pair -6, 5. So that what that's saying is, if we graphed a vector in standard position starting at the origin, and it went 6 to the left and 5 up, it would be equal to this vector DE. It would just be parallel to it and shift it around just a little bit. Okay, second question is, find the magnitude. Well, magnitude is written as the absolute value of vector DE. And we know that that magnitude can be found by using this distance formula here, right? Well, if we use the distance formula, notice we've already found x2 minus x1 and y2 minus y1 when we found the ordered pair. So essentially what -6 and 5 are the x2 minus x1, the y2 minus y1, or the a and b. So then when I find the magnitude, I'm just going to take the square root of, if you want to call this, a squared plus b squared. So that's going to be -6 squared plus 5 squared. Okay, well that's going to equal the square root of 6 squared, negative 6 squared is going to be positive 36. Be careful with that, by the way. 5 squared is 25, and that's going to be equal to the square root of 61. Now, 61 is a prime number, so I know there are no other factors in it, particularly no other square factors, but you have to make sure that your answers, whenever you find the magnitude, must be simplified radicals. Must be simplified radicals. So no decimals. Your magnitude will always be in the form of a radical. If a square number can be pulled out of it, you need to do that as well. Okay, in this case, 61 does not. Number 2, find the following operations if, and then I'm going to give you some vectors to define. So let's say if vector m, and I'm going to put my vector symbols back on the top when I get my pen again. I'll say vector m is at 5, 7. Vector n is at 0, 4. And vector p is at 1, 3. Oh, let's make it black. Okay, so these are my 3 vectors, m, n, and p. Now, when I ask you for operations, these are exactly what you think they might be, and they're as easy as you think they might be as well. So we're just going to do a few examples here. For part A, if I ask you for vector m plus vector p. Now, we discussed earlier what this looks like geometrically using the parallelogram method or the triangle or tip-to-tail method. Algebraically, what this is doing is literally just adding your numbers. So you're going to take your coordinates for vector m and add them to the coordinates of vector p, and voila, you're going to have the sum. So this will look like the x coordinates for m is 5, plus the x coordinate for p is 1, and then negative 7 plus 3 are the y coordinates, giving us the sum of 6, negative 4. So if I add vector m and vector p, I get this vector represented by 6, negative 4. Okay, that's adding them. We can also multiply by a scalar. So it's not multiplying like m times p or something like that, but just by a scalar. So if I ask you what is 7 times vector p, then this is as simple as multiplying both the coordinates of vector p by 7. So this is just going to be 7 times 1 times, comma 7 times 3, which is the vector 7, 21. Now, mathematically, those are very simple, and on those occasions, I'd actually be fine if you didn't show work. However, anytime I do something a little bit more complicated, I'd say 3 or more terms, I would like to see what you're doing, because it's also going to prevent you from making a mistake. So if I ask you for 2 times vector m plus 3 times vector n, they must see a squirrel, minus vector p. Puppies! We're trying to learn. Then you kind of want to take this one step at a time. Okay, this is going to equal 2 times vector m. So let's write that out. That'll be 2 times 5, 7, plus 3 times vector n will be 3 times 0, 4, minus vector p, which is 1, 3. Okay, we can distribute those scalars. So it's going to be 10, 14, plus when we distribute that 3, that's still just going to be 0, but then 12, minus 1, 3. And where people tend to mess up is anytime subtraction is involved, because you have to realize that that negative sign essentially just distributes to both those numbers inside. Okay, so then you take the x value from each one to get your first number. So it's going to be 10 plus 0 minus 1, and then all of the y's. So that'll be 14 plus 12 minus 3. I feel like that should be a negative 14. I feel like, oh yes, I'm sorry. This should have been, it's okay. I had a negative on my notes example earlier. Oh, and look, I put a negative up here in example A. So look, for the sake of this being consistent, that way we didn't mess up example A, I did write a negative. This vector M up in the question should be negative as well. So vector M should be 5, negative 7. So if you wigged out on me for example A, that's why. So here, again, I want to go ahead and make, let's edit these here. So in the first one, that'll be negative 7. That means this will be negative 14. So then when I do negative 14 plus 12 minus 3, when we simplify both of these statements, I get 9, negative 5 for that one. Okay, so that's how you do operations. The last example is going to say something like this. It's going to say write vector AB as the sum of unit vectors for point A, which is at 4, negative 1, and point B, which is at 6, negative 2. So it says write AB, or sorry, this should say vector AB, as the sum of unit vectors. So what this is meaning is instead of me just adding A and B, so we want to find the sum first, actually. Let's go ahead and do that. So if I want to find the sum, then I need to, well, actually, I'll come back to that statement in a second. We need to figure out first, how do you represent the vector that is between A and B? And it's just like we did for this first example. If I give you two coordinates, you're essentially going to find the change in X and the change in Y to represent that vector. Okay, so vector AB is going to be represented by the change in X, so X2 minus X1, comma, Y2 minus Y1. Oh my gosh. We are not threatened. Hey, we're not threatened. I'm sorry, y'all. I guess it's no different if I were teaching live. All right. So then X2 minus X1, again, you want to do direction. So since A is our initial point, we want to call this, hey, X1, Y1, and then B will be X2, Y2. So X2 will be 6 minus 4, and then that'll be negative 2 minus negative 1. Come see. So then 6 minus 4 is 2. Negative 2 minus negative 1, that'll change to plus a positive, and that'll be negative 1. Okay, so this is vector AB, just as what we represent it by. The question is, write this as a sum of the unit vectors. So if you recall, the unit vector in the X direction is I, and the unit vector in the Y direction is J. So if I want to write it as a sum of unit vectors, then all that means is that I'm going to take the extra, if this vector were being graphed, and I want to write it as if I and J were being added and multiplied by a scalar somehow, then we would say that vector AB could also be written as 2 times vector I. You can do plus negative 1 or just minus 1 times vector J. And because it's 1, we don't need to write that. So this is a sum of the unit vectors. So step 1 is to actually find what the vector ordered pair would be, given the ordered pair for A and B, and then take your unit vectors, X and Y, which are they just stand for 1, but write them as the sum, and then you'll get your vector AB written as the sum.